Phone's ringing.
You better answer it. Alternative bootstraps.
What are we going to do with residuals if it's bootstraps?
We're looking for those wild blocks, remember?
Oh, yeah, wild blocks.
I think we should just call the parametrics.
'Cause it's your bread and butter, baby. What's your jam?
Greetings, Bios 6618. In this lecture, we're going to do a brief survey of advanced Bootstrap topics. We'll first start with a brief review before discussing alternative confidence interval calculations, as well as other types of bootstraps that are out there beyond the case-resampling we've discussed in class. So let's start with a brief review. Remember, when we covered the two-sample bootstrap, we're really thinking of this idea of nonparametric case-resampling. Now, assuming here we have two populations, we're randomly going to take a sample from each in the real world, so a bootstrap will mimic that process. Essentially, if we have two samples of size m and n from two populations, we're going to follow this algorithm we see on the slide here, where we'll start by redrawing with replacement within each group the same size m and n respectively, and then compute whatever statistic we're interested in to compare the two groups. We'll do this over and over, let's say 10,000 times, and then we'll construct the bootstrap distribution of our statistic, and we can inspect things like its spread, bias, and shape. With our case-resampling bootstraps, here's kind of an overview of the topics we reviewed that you're welcome to go back to see in past lectures. We looked at both one and two sample problems. We also looked at different ways we can summarize that variability by calculating the standard error for a statistic, or the bootstrap percentile confidence interval, or normal percentile confidence interval. However, we did mention or we've seen some potential limitations, and the bootstrap world is much, much larger than we've encountered so far. In this lecture, we'll introduce some advanced topics to discuss some alternative strategies. The first set of alternatives we're going to look at are different or improved upon confidence interval calculations relative to that bootstrap or normal percentile interval. So as a quick refresher, we do have that bootstrap percentile confidence interval, which is extremely easy to implement. In other words, we just take the alpha over 2 and the 1 minus alpha over 2 percentiles of our bootstrap distribution. But the trade-off is that even though it's entirely nonparametric and makes no assumptions, it might be inaccurate. Or in other words, we have that rule of thumb where you can take the absolute value of the bias of our bootstrap distribution divided by the standard error. And if it was less than 0.1, we felt pretty good about its accuracy. Although if it was greater than 0.1, that's where we were concerned that it might be inaccurate. On the other hand, we had a normal percentile confidence interval estimate that used the standard error from our bootstrap distribution, but ultimately made an assumption about normality in calculating the interval and test statistic, and it also may be inaccurate in different ways. For example, the summary we did here is that we calculate the coverage in each tail, knowing that theoretically a normal distribution, if appropriate, should have symmetry, and if we depart from that alpha over 2 coverage or rate in each tail, we'd expect there's some other form or interval that might be more appropriate. In contrast, there are, as I've alluded to, many other types of confidence intervals out there that have been proposed to improve our estimation, and we'll talk about a few of those today. The first is known as the bias corrected or BC interval. Now, just the general idea here behind this BC interval is to adjust our bootstrap percentile confidence interval to account for potential bias. Now, to get slightly more technical here, it's actually built on the idea that an estimator, let's say theta hat, may not be median unbiased. This is very similar to the concept of mean unbiasedness, where we would say that something is not biased or it's unbiased if the expected value of theta hat is equal to theta, but it's applied instead of to the mean to the median. Now, the interesting thing here, though, is that deviations from median unbiasedness can actually be estimated in our bootstrap, since we're actually assuming that the theta hat from the sample is the true value that we're comparing our bootstrap distribution to. Efron proposed a median bias corrected interval, that ultimately is known as this bias corrected interval, that allows for a shift in the distribution, which we call g of theta hat, by some unknown amount z, which in our bootstrap setting represents the equation we see below, where we see a connection here to a standard normal distribution of phi of x. Now, in addition to a bias corrected, there's also a bias corrected accelerated or BCA interval. This is a second improvement proposed by Efron also. It attempts to account for underlying higher order effects so that it corrects the Bootstrap percentile interval for both biased and for skew. In other words, it has this idea of adding this acceleration constant A that is related to the third moment skewness coefficient. And again, we're not going into too many details today, just introducing that these exist and so some code examples of doing it. But we have this general formula here below, which again shows a connection to some assumptions of parametric normality in some of these estimations. Another type of interval that's out there is the studentized t interval, and this can also be known as the Bootstrap t interval, and it's another alternative approach to estimating confidence intervals. Essentially here we're estimating the quantiles from the Bootstrap distribution of the student's t-test. So this is kind of like an improvement I would think of as the normal percentile interval, where we actually have this quantity here instead of assuming, let's say, a standard normal distribution and something like maybe 1.96 for alpha of 0.025 in each tail. Well, we're actually going to add another layer of bootstrapping to estimate the t-distribution for our statistic to use in the interval calculation. Now, specifically, we outline here that theta hat will be that estimate from our sample. As I mentioned as well, t star will be the 1 minus alpha over 2 percentile based on the Bootstrap student's t-test. In other words, for each iteration in our t-test, we'll calculate a t star here where you have to calculate the standard error in each situation. If we're looking more generally at the standard error that's actually showing up within the formula, that will be our estimate from the sample, whereas the standard error where we add another little hat and a star to the theta corresponds to our t-star calculation. Now, the interesting thing here is that the resulting intervals don't have to be symmetric, since we note that t star of 1 minus alpha over 2 doesn't have to equal negative t star of alpha over 2 because it's estimated from our bootstraps. And this is an improvement over the normal percentile. The limitation or downside here, though, is that it can be influenced by outliers, in which case the percentile intervals we've discussed already may be a more appropriate choice. So let's see a quick example of at least the Bootstrap percentile interval approaches here. We're going to leverage the dataset from the American Statistical Association's section on teaching statistics in the health sciences and their blood storage dataset. We're interested in comparing the mean preoperative prostate-specific antigen, or PSA, between two groups of tumor stages, earlier stage 1 to 2A versus later stage 2B to 3. We can note here that the distributions look like there is some sort of a right skew here, as well as unequal or different standard deviations in each group, as well as imbalanced sample sizes, which may make us worried about, let's say, doing a parametric t-test. For the sake of our example, we're going to calculate our confidence intervals leveraging the boot package in R, where we of course will set our seed for reproducibility. Now, with the boot package, we do have to define our sampler or statistic estimate in the form of a function. And so here we see that we have this with the first argument being the data set and the second argument essentially being the index that we'll be using for resampling. We then see within the function itself, we will calculate the mean by resampling amongst the lower tumor group and the upper tumor group settings, and we will ultimately return the difference of those two group means. From there, it's pretty easy to implement this function. We use boot, giving it our data set, the function we just created, mean diff, for our statistic, and we're going to say that we have 10,000 bootstrap iterations. Once we run that object, we can feed it into the boot.ci function. Now, by running it here, we see that we get some intervals we're already familiar with, such as the normal and the percentile intervals. We also then have our new bias-corrected accelerated interval, BCA. One thing you'll notice is not present is the studentized t, or the bootstrapped t distribution interval. And that's because it would require us to add some complexity to our sampling function beyond the scope today to estimate the variability or that standard error for use in estimating those statistics. What we can note here is that when we compare the BCA and the percentile, since the BCA is an attempted improvement upon the bias and skewness potentially present in the percentile interval, we do see that the BCA seems to pull down both of the estimates relative to the percentile, where the lower estimate goes from -9 to -9.6, And the upper estimate in the percentile decreases further from negative 1.56 to negative 1.9. So we do see that there's a slight shift, and there's some evidence to show that the BCA may actually be, in some cases, also narrower and more precise relative to the percentile. But here we see an example of how we can get our statistics and our interval calculations, especially for some of these more complex formulas, by leveraging software like the Boot package. For the last few minutes, we're going to do a quick survey of just other types of bootstraps and highlighting some of the considerations and approaches for them. Everything we've really focused on thus far has been this idea of a nonparametric case resampling bootstrap approach, which admittedly is fairly straightforward and works for many problems. However, there are many other approaches to bootstrapping out there. And in this section, we'll touch on some of the more common ones you might encounter and some of their general details. And the first to point out is a parametric bootstrap. Now this is interesting. This is the exact opposite of that nonparametric one, because we're actually going to make assumptions that our data comes from a known distribution but with unknown parameters. The idea is that one can then estimate your unknown parameters from the available data and then use the simulation to actually generate new samples to estimate the variability of. Now, this approach works really well if you have a strong reason to believe the data follow a particular distribution, resulting in more accurate estimates of your standard error and confidence intervals. And this is especially true if you have smaller sample sizes where a nonparametric bootstrap may struggle. The trade-off we're making here, though, is if our assumed distribution is wrong, it can lead to actually less accurate estimates and other issues. There are some general steps we can follow, just like we have for our nonparametric bootstrap, though. The first step is in assuming that our data x1 to xm are all drawn from a parametric distribution that we are trying to maybe make some assumptions or estimate about the f of theta. We'll then estimate theta by some statistic from our sample theta hat. For example, for the mu population mean, we might use the sample mean x bar. In many cases, people propose using MLEs, but you could also use method of moments or any other estimator for your statistic to plug in. From there, we'll generate B bootstrap samples, in this case now by simulating data from f of theta hat. So in other words, here we might simulate m new cases from a normal distribution with mean x bar, maybe an estimated variance s squared. And we'll then calculate our statistic of interest theta star for each bootstrap sample. We'll then use those B bootstrap estimates to estimate things like our standard error confidence interval, just like we would for the nonparametric bootstrap, just that we have a different approach with some parametric assumptions along the way. Another alternative is known as a smoothed bootstrap. We know or have noted that nonparametric bootstraps do not always work so well for rank-based estimators such as the median, which just essentially take one or two data points to get the summary. One potential solution you can do is to actually add a small amount of zero-centered random noise to each resampling observation in each of your B bootstrap samples. In other words, smoothing over some of this rank-based estimator nature of the data. In practice, you can use any estimator you want, but some common choices include the uniform, maybe from negative delta to positive delta, or a normal distribution, again centered at 0 with standard deviation or variance delta, where delta would be set depending on your context. The thing we have to think about is that if you set it to be too small, not enough smoothing will occur, but if you set it to be too large, it'll obscure the original information. So you have to find this kind of fine balance and maybe even play around with that parameter in some cases. Now, like before, the results after you do this little tweak or shift of the random noise can be summarized to estimate the standard error or confidence interval, just like you would for any nonparametric bootstrap. We also have an idea known as residual bootstraps, and this specifically is in the context of linear regression models, where we might actually be interested in treating our predictor variables x in the model as fixed rather than random, which is implicitly what we're actually assuming when we do case resampling, which also generally works for bootstrapping regression models. Now, an easy way to address this choice, so if you really do want to keep your x variables fixed, or because maybe you designed a study that had certain parameters set in advance, we can actually do this by resampling on the residuals using these 4 following steps. So the first thing we'll start by doing is fitting our model, and we'll keep our predicted value y hat I. We'll also calculate and predict our residual for each observation, e hat I. Then for each observation set, y sub I with all possible predictors that someone may have, x sub 1 up to x sub m, We'll then add a randomly resampled with replacement residual to the fitted value. So here it's a little funky in notation, but essentially we're getting a new predicted outcome or value to use based on adding the predicted value for a person plus some randomly sampled residual from the data set. We'll then refit our regression model with our outcomes yi star and save the statistics of interest. So for example, the beta coefficients or the R squared or adjusted R squared summary. We'll then repeat this b times. The results can then be summarized as before, just with the standard error confidence intervals, just like a nonparametric bootstrap. But in this case, we've gone to this extra step to treat our x's as fixed, which again may better reflect our study designer setting, and again can also be advantageous in potentially smaller sample sizes. Another twist of this residual bootstrap is the idea of wild bootstraps. And this literally builds off of this idea here, but not just by adding a randomly resampled residual value, but also by multiplying that by a randomly sampled random variable v sub I, which will have mean 0 and variance 1. Now, essentially, we follow the exact same steps we had on the slide before. We'll fit our model, we'll keep our predicted outcomes y hat and the residuals for each person e hat. For then each person, we'll add a randomly resampled replacement residual to the fitted value, but in this case, we'll also multiply it by this vi, which will also be randomly sampled from a distribution. We then refit the regression model with this new y star I and save our statistics of interest and repeat this b times. There's lots of choices you can use for vi, but common ones include a normal distribution with mean 0, variance 1, or something known as Mammon's two-point distribution, which essentially samples from two different points with about a 70 to 30 split probability and has some interesting properties. But once again, when all this is said and done, the results can be summarized to estimate your standard error confidence interval, just like the nonparametric bootstrap. And this may help to better reflect, especially if we have issues, like we mentioned at the top here, with the assumption of homoscedasticity in our regression model, with actually fitting this bootstrap and estimating our parameters more accurately. So in this short lecture, we examine alternative approaches to calculating confidence intervals, including adjusting for the bias or bias and skewness. We also briefly reviewed some alternative bootstrap strategies that may be used in certain contexts, and oftentimes we'll have software available that you can find by searching in R, SAS, or other places to implement them. It's also worth noting here that while we've done a lot of different bootstrap things this semester, there are still even more bootstrap approaches and confidence interval strategies for the bootstraps that might be helpful in different contexts or settings. So definitely keep your eyes out for others, and keep your eyes out for other videos talking about other topics for our class, where I look forward to seeing you again in the future.